Hey guys, and welcome to my lecture on Fourier transform examples. In this tutorial, I will solve lots of examples to show you how to use table of pairs and table of properties to find Fourier transform. This tutorial is extremely important, so you need to concentrate 100% and please make sure that you practice each example with me. If you do that, by the end of this tutorial, you can call yourself master of Fourier transform, I promise. Let's start. First example. If the Fourier transform of xt is x omega, what is the Fourier transform of x3t minus 3? In this example, we want to practice time shifting and time scaling properties. As you recall from the last lecture, when the signal gets shifted in the time domain by t0, in the frequency domain it gets multiplied by a complex exponential function. Also, this is time scaling property, which shows the inverse relation between time and frequency domain. To find Fourier transform, it's easier to start with the time shift and then consider time scaling. This is the time shift, so if xt gets shifted by 3 units, t0 is 3, and we just need to multiply x omega with this exponential. Now let's consider time scaling. In this case, a is 3, so we just need to multiply xt by this factor and replace omega by omega over a. A is 3, so we just need to swap omega by omega over 3. Here we go. This is cancelled by this, and let me write it again. Absolute value has no effect on the positive number, so here's the final answer. Done. So keep this in mind. When we have time shifting and time scaling, first consider the time shift and then go for time scaling. Easy peasy. Next example. If Fourier transform of xt is x omega, find the Fourier transform of this signal. Let me write the time shifting property here. In this example, basically we have two time shifts. For the first signal, t0 is 2, so here's the Fourier transform. For the second signal, t0 is minus 2. Please note there is a minus sign here. So to use this property, you can write t plus 2 as t minus minus 2. This guy is t0, and here is the Fourier transform. Last step, we need to add them up. X omega is the common term, so let's factor it out. Here we go. As you recall from the complex numbers lecture, cosine function can be presented in this form. Here 2 is missing at the bottom. So divide the whole thing by 2 and multiply it by 2. Basically it's the same thing. 2 can be cancelled by 2. Now you can call this term cosine 2 omega multiplied by the rest. Done. Next example. Find the Fourier transform of this signal. As we learned in the last lecture, the Fourier transform of this signal, where a is constant, is 1 over j omega plus a. In this example, a is 2, so here's the Fourier transform. Now to create this signal, we just need to shift the time by 1 unit, i.e. we need to replace t by t minus 1. Now we need to use the time shifting property where t0 is 1. Here we go. Let me write it in a neat form. Done. Next example. Find the Fourier transform of this signal. Look at this signal carefully. Here t is shifted by 1 unit, but here there is no time shift. So we cannot use time shifting on this signal as we did in the last example. To deal with this problem, I'm gonna create the time shift. Let's write t as t minus 1 plus 1. It's the same thing. Now let's break this exponential into two terms. This number is constant, so bring it to the front. To find Fourier transform, don't worry about this constant. We can apply it at the very end. Now, look at this signal again. We have the same time shift here and here, and therefore we can use the time shifting property. Similar to the previous example, first I'm gonna use this pair to find Fourier transform. Here we go. Now shift the signal by 1 unit and apply the time shifting property where t0 is 1. So we just need to multiply Fourier transform by this complex exponential. Finally, we need to consider this constant. So multiply both sides by this term. Combine these two. Here is the final answer. Done. Next example. Find the Fourier transform of e to the power of minus 3 absolute value of t. As I explained before, absolute value of t is equal to t when t is positive and minus t when t is negative. For instance, absolute value of 3 is 3 because it's a positive number. But to find the absolute value of minus 3, we need to multiply it by a negative sign. So you can write this function as a combination of two terms, one for positive t and one for negative t. When t is positive, we can ignore the absolute value. But I'm saying t is positive, so we need to make sure this term is valid just for positive t. To do so, I'm going to multiply it by u of t. This function is equal to 1 for positive t and it's 0 for negative t. When t is negative, absolute value of t is minus t. So we get this. But I'm saying t is negative. So we need u of minus t to make sure this term is just 1 for negative t. Now let's find Fourier transform. To find the Fourier transform for the first term, we can directly use the pair from the table of pairs. To find the Fourier transform for the second term, we need to use the time scaling property. So here's the Fourier transform of the first term. Now let's consider the second term. Think about it. If this signal is x of t, this is basically x of minus t. To find the Fourier transform for x of minus t, we can easily use this property where a is minus 1. This is equal to 1. So to find the Fourier transform for x of minus t, we just need to replace omega by minus omega. That's it. Here we go. Last step. Let's add them up. To simplify the answer, I'm going to add the rational terms. Minus j omega is cancelled by j omega. Let's also simplify the denominator. First multiply j omega by minus j omega. J is a square root of minus 1. So j multiplied by j, we get minus 1, which is cancelled by minus sign here. So we get omega squared. Then multiply j omega by 3. Finally multiply 3 by the second parenthesis. Here we go. These two cancel out each other and we get omega squared plus 9. So the Fourier transform of this function is 6 over omega squared plus 9. Done. Let's move on to the frequency shifting property. If xt is multiplied by a complex exponential function where omega naught is constant, the frequency spectrum gets shifted by omega naught. Example. If Fourier transform of xt is x omega, find Fourier transform for this signal. To solve this example, first we need to shift the time by 1 unit to the left and apply the time shifting property. Then we need to multiply the signal by this complex exponential and use the frequency shifting property. Let me add the time shifting property here. Okay, we are all set. The first step, apply the time shift. Again, there is a negative sign here, so to use the property, write this as t minus minus 1. So t naught is minus 1, which is cancelled by negative sign here. Here is the Fourier transform. The second step, multiply the signal by this complex exponential function and use the frequency shifting property where omega naught is 3. So we need to shift the frequency spectrum by omega naught, i.e. we need to replace omega by omega minus 3 in this function. Here we go. Done. Next example. If this Fourier transform pair is given, what is the Fourier transform of this signal? To go from this signal to this signal, first we need to shift t by 3 units. Then we need to scale t by 5 units. And finally, we need to multiply it by this term. Before I start, let me add the time scaling property here. First step, shift t by 3 units to the right. T0 is 3. So we just need to multiply the Fourier transform by this term. Here we go. Second step, scale time by 5 units and use the time scaling property. A here is 5. So we just need to replace omega by omega over 5. Here's what we get. Let me write it in a neat form. This is equal to 5. Bring 3 to the front and apply a square to the parentheses. Now we are done with this part and we just need to consider this complex exponential term as the last step. So multiply the signal by e to the power of minus j3t and use the frequency shifting property where omega naught is minus 3. So we just need to replace omega by omega minus 3 or omega plus 3. Here we go. Done. Let me recap the order. First, I applied the time shift, then time scaling, and finally frequency shifting. Let's consider these properties again and solve one more example. This Fourier transform pair is given, and the question is, what is the Fourier transform of this signal? To convert this shape to this shape, first we need to shift t by 6 units to the right, and then scale t by 4. Finally, multiply the signal by this complex exponential function. Let's start with the time shift by 6 units. This is t0, so we just need to multiply Fourier transform by this term. Here we go. Next step is time scaling by 4. So this is a, and we just need to multiply the Fourier transform by this factor. Also, we need to replace omega by omega over a, where a is 4. Here we go. Let's simplify the answer. This is equal to 4. Bring this constant to the front and bring 6 here. And also apply the square to the parentheses. By multiplying these two, we get omega squared over 64. Last step is to multiply the signal by this complex exponential function and use the frequency shifting property where omega naught is 7. So we need to shift omega by 7 units. Here we go. Done. Again, let me emphasize the order. First time shifting, then time scaling, and finally frequency shifting. So far, we have seen these properties and practiced how to use them. The next properties that I want to cover are time differentiation property and also frequency differentiation property. Example. If Fourier transform of xt is x omega, what is the Fourier transform of this signal? This is super easy. First multiply xt by this complex exponential and use the frequency shifting property. Then apply derivative and use the time differentiation property. That's it. First, let's multiply xt by the complex exponential and use this property where omega naught is minus 5. So you just need to replace omega by omega minus 5, which is omega plus 5. Then apply derivative in the time domain and use this property. So you just need to multiply the frequency spectrum by j omega. Done. Next example. If Fourier transform of xt is x omega, what is the Fourier transform of this signal? To create this signal, first we need to shift the time by 1 unit. Then we need to apply the second derivative to xt minus 1. The second derivative is basically the derivative of derivative. So to solve this example, first I will shift the time by 1 unit and then I will apply this derivative. And finally, I will apply the derivative one more time. First, let's shift the time by 1 unit and use this property where t0 is 1. Here's what we get in the frequency domain. Now, let's apply the first derivative to our signal. Based on this property, we just need to multiply the frequency spectrum by j omega. Finally, let's apply this derivative to the signal in the previous step and use the time differentiation property again. So we just need to multiply the frequency spectrum by another j omega. Here we go. J omega multiplied by j omega, we get j omega squared multiplied by the rest. Done. Next example. What is the Fourier transform of t rect t over 2? Rect stands for the rectangular function. Based on the table of pairs that we learned in the last lecture, the Fourier transform of rect t over capital T is this. In this example, capital T is 2. So let's replace it by 2. 2 is cancelled by 2 and we get this. The last step is to multiply the rectangular function by t. Here we go. Now we can use the frequency differentiation property and here's the answer. Done. Next example. Find the Fourier transform of sine t. As you know, sine function is -1 for t less than 0, 0 at the origin, and 1 for positive t. To use the Fourier transform for this function, I'm going to use a simple trick. Let's apply derivative to this function. For negative t, the function is constant, so the derivative is 0. The same story for positive t. The only place that the derivative is not 0 is at the origin, when there is a jump from -1 to 1, i.e. 2 units. So the derivative of sine t is equal to 2 delta t. Now I'm going to use this equation and time differentiation property to find Fourier transform of sine t. Let's say the Fourier transform of sine t is x omega. The whole purpose in this example is to find x omega. To do so, let's apply derivative to sine t. Based on the time differentiation property, we just need to multiply x omega by j omega. Also, we know the derivative of sine t is equal to 2 delta t. Based on the table of pairs that we learned in the last session, Fourier transform of 2 delta t is 2. From this equation, we know these signals are equal. This means their Fourier transform must be equal. Therefore, x omega, the Fourier transform of sine t, is 2 over j omega. Let me write the final answer again. Fourier transform of sine function is 2 over j omega. Done. Next example. If the Fourier transform of sine t is this, what is the Fourier transform of unit step function? Let me plot the sine t again. Also, as we know, unit step is 0 for negative t and 1 for positive t. Now, if we compare the shape of sine t with u of t, we can easily conclude that u of t is 1/2 sine t plus 1/2. Let me show you why. The first step is to scale the amplitude by 1/2 unit. So -1 goes to -1/2 and 1 goes to 1/2. Then add the amplitude by 1/2. So this goes to 0 and 1/2 goes to 1. This is basically unit step. So unit step can be represented in this way. Now to find the Fourier transform of u of t, I'm going to use this equation. The Fourier transform of sine t is given 2 over j omega. Let's multiply both sides by 1/2. Here we go. 2 is cancelled by 2. Now let's find the Fourier transform for this constant. Based on the table of pairs, we know the Fourier transform of 1 is 2 pi delta omega. Let's multiply both sides by 1/2. 2 is cancelled by 2 and we get this. Last step, let's add them up. So the Fourier transform of ut is the summation of these terms. Done. Let me write it one more time as the Fourier transform of ut is very useful. Next example. If this pair is given, what is the Fourier transform of this function? In this example, I need to use time scaling and frequency differentiation properties. To go from this shape to this shape, first we need to scale t, then we need to multiply the signal by t. There is only one small problem here. Pi is multiplied by t squared, not t. To use the time scaling property, we need to apply the scaling factor to t. So Let's write it like this. It's basically the same thing if you apply the square to the parentheses, a square root of pi becomes pi. So this is the same thing, but in this presentation, a square root of pi is applied to t. To solve this example, first I'm going to scale time by a factor of a square root of pi and use the time scaling property where a is this. So we need to multiply Fourier transform by this factor and replace omega by omega over a in this function. Here's what we get. This is cancelled by this. Also, let's apply the square to the parentheses. So we get this. Then we need to consider this term. So let's multiply our signal by t and use frequency differentiation property. Done. The next properties that I'm going to cover are the time domain convolution and frequency domain convolution. If you convolve x1t with x2t in the time domain, you get multiplication in the frequency domain. On the other hand, if you multiply x1t with x2t in the time domain, you get convolution in the frequency domain. First example. If the Fourier transform of xt is x omega, what is the Fourier transform of t xt squared? This is super simple. You can write a squared as xt multiplied by itself. Now we have multiplication in the time domain. So we have convolution in the frequency domain. The last step is to multiply the signal by t in the time domain. Now we can use frequency domain differentiation property. Here we go. Done. Next example. If the Fourier transform of xt is x omega, what is the Fourier transform of xt multiplied by cosine 5t? We have multiplication between xt and cosine 5t in the time domain. So this means that their Fourier transform is convolved in the frequency domain. The Fourier transform of xt is given, i.e. x omega. The Fourier transform of cosine function based on the table of pairs is this. A summation of two delta functions. Now, if we multiply xt by cosine 5t in the time domain, we just need to convolve their Fourier transforms. The Fourier transform of first signal convolved by the Fourier transform of the second signal, which is this. Pi is cancelled by pi. As you may remember from the convolution examples tutorial, by convolving a signal with a shifted delta function, you will get a shifted version of x omega. Here, I'm convolving x omega by two delta functions. X omega convolved by delta omega minus 5, we get x omega minus 5. X omega convolved by delta omega plus 5, we get x omega plus 5. So here's the final answer. Multiplying signal by cosine or sine function is called modulation and has tons of application in the communication systems. In fact, we use a sinusoidal function to carry a message, i.e. xt, from one point to another. I will dedicate one full lecture to modulation to make it crystal clear, so don't worry about it for now. Next example. What is the Fourier transform of this signal? Let's bring ut, unit step function, here, so I can use table of pairs for the exponential part. Now I have a multiplication of two signals in the time domain. Based on the table of pairs, the Fourier transform of this exponential function is 1 over j omega plus 5. Also, according to the table, the Fourier transform of sinusoidal function is this. Again, we are multiplying these two in the time domain, so we need to convolve their Fourier transforms in the frequency domain. The Fourier transform of the first signal, which is this, convolved by the Fourier transform of the second signal, which is this. Pi is cancelled by pi. Let's bring j here and write it again. Again, to convolve x omega with a shifted delta function, we just need to shift x omega, or basically replace omega by omega minus omega naught. So, to convolve this by the first delta function, we just need to replace omega by omega minus 2. And to convolve with the second delta function, omega is replaced by omega plus 2. That's the final answer. Done. Next example. If the Fourier transform of xt is x omega, what is the Fourier transform of the derivative of xt convolved by the exponential to the power of 2jt xt? This is super easy. First, let's apply the derivative to xt and use time domain differentiation property. Then, multiply xt by this complex exponential function and use frequency shifting property. Finally, consider the convolution in the time domain, which is multiplication in the frequency domain. Let's start with the derivative. Based on the time domain differentiation, we just need to multiply Fourier transform by j omega. Now, let's multiply this complex exponential by xt and use the frequency shifting property where omega naught is 2. So, you just need to replace omega by omega minus 2 in the frequency domain. Here we go. Finally, we need to consider convolution between these two terms. Convolution in the time domain is multiplication of the Fourier transforms in the frequency domain. The Fourier transform of the first term is this, multiplied by the Fourier transform of the second term. Done. Next example. If the Fourier transform of xt is x omega, what is the Fourier transform of this signal? To solve this problem, first I'm going to consider time scaling by minus 2, then time shifting by 1, followed by a time scaling by 3. Next, convolution between these two terms, and finally, I will apply the derivative. This is super simple. Let's start with this term and use the time scaling property where a is minus 2. To use this property, we need to replace omega by omega over minus 2. So here's what we get. The absolute value of minus 2 is 2. Now let's consider the second term. First shift t by 1 unit and use time shifting property. In this property there is a negative sign here. So write t plus 1 as t minus minus 1. Now this guy is our t naught, which is cancelled by the negative sign here. So we get this. Next step, scale the time by 3 units and use time scaling property where a is 3. Based on the property, you need to replace omega by omega over 3. The absolute value of 3 is 3. Now the Fourier transform of this guy is here, and the Fourier transform of this guy is here. Next step is to consider convolution between two terms, which means multiplication of their Fourier transforms in the frequency domain. Here we go. To simplify the answer, multiply this constant by this and bring the exponential to the front. We still need to go one step further, i.e. applying derivative in the time domain to the signal. Based on the time domain differentiation property, we just need to multiply the Fourier transform by j omega. Here we go. Done. Next example. If the Fourier transform for this pair is given, what is the Fourier transform of this signal? This is very easy. We already know the Fourier transform of this signal. It's given. Also, based on the table of pairs, we know the Fourier transform of cosine function. So we just need to multiply both signals in the time domain and use convolution property in the frequency domain. Then we need to apply derivative to the signal and use time domain differentiation property. That's it. Based on the table of pairs, the Fourier transform of cosine t is this, the summation of two delta functions. Now to generate this big guy, let's multiply exponential with cosine t. Multiplication in the time domain is convolution between x1 omega and x2 omega in the frequency domain. This is x1 omega and this is x2 omega. Pi is cancelled by pi. Again, convolution with the delta function just shifts the signal. So to convolve this term by the first delta function, we just need to shift or replace omega by omega minus 1, easy peasy. Same story for the second convolution. Finally, we need to apply derivative in the time domain and use the time domain differentiation property, i.e. we just need to multiply Fourier transform by j omega. Done. Next example. What is the Fourier transform of this signal where the line equation is t plus 1 here and minus t plus 1 here? To solve this example super fast, I'm gonna use a nice trick. We can easily show this signal is the convolution between rectangular function by itself. As you may remember, the rect of t is a window which is 1 from -1/2 to 1/2. If you convolve rect t with itself, you will get this triangular shape. This convolution is super simple, so please pause the video and do it yourself. If you have problem to do that, please watch my tutorial on the convolution examples. So you can represent this signal in this form and solve this example super fast. Based on the table of pairs, we know the Fourier transform of rect t is sinc omega over 2. We have another rect t here. The Fourier transform is basically the same. Now let's convolve two rectangular functions. Convolution in the time domain is multiplication in the frequency domain. So we get sinc omega over 2 squared. Done. Next property that I want to cover is the conjugation property. Example, if the Fourier transform of xt is x omega, what is the Fourier transform of t x5t minus 1 conjugate? To solve this example, first I use the time shifting property. Next, time scaling property. Then conjugation, and finally multiplication by t, which is basically frequency domain differentiation. Let me write all the properties that I need here. First, let's start with the time shift. The Fourier transform of xt is x omega. Now shift time by 1 unit and use the time shifting property where t0 is 1. So you just need to multiply the Fourier transform by this complex exponential. Next step is to scale the time by 5 units and use the time scaling property where a is 5. So omega is replaced by omega over 5. Here we go. Now let's apply the conjugate to our signal in the time domain. Based on this property, we just need to replace omega by minus omega and apply conjugate to the Fourier transform. Let's replace omega by minus omega. The absolute value of 5 is 5. This negative sign is cancelled by minus omega and we get this. Now let's apply conjugate. Conjugate has no impact on the real number. Also, to apply conjugation to a complex exponential function, we just need to switch the power sign. Here we go. The last step is to multiply the signal by t in the time domain and use the frequency domain differentiation property. Here is the final answer. Done. Next example. If xt is a real and even signal, prove the Fourier transform is real. We know xt is real. This means xt is equal to its conjugate. In fact, conjugate has no impact on the real numbers. For instance, 1 is equal to 1 conjugate, or 3 is equal to 3 conjugate. Now apply Fourier transform to both sides of this equation and use the conjugation property. So we get x omega is equal to x conjugate minus omega. Also, xt is even. From my lecture on the signal properties, we know for an even signal xt is equal to x minus t. Apply Fourier transform to both sides of this equation. To find the Fourier transform of x minus t, let's use time scaling property where a is minus 1. The absolute value of minus 1 is 1. So we just need to replace omega by minus omega. Here we go. Now compare these equations. The left sides are equal. This tells me the right sides must be equal. To get rid of the negative sign in both arguments, let's replace omega by minus omega. Here we go. Now look at this equation carefully. X omega conjugate is equal to x omega. This tells me x omega must be real as the conjugate has no impact on the signal. Done. Next example. If the Fourier transform of xt is x omega, what is the Fourier transform of t minus 1 to the power of 100 multiplied by xt minus 1 conjugate? To solve this problem, let's apply conjugate first and use this property. Now let's multiply the signal in the time domain by t and use the frequency differentiation property. In this example, the power for t is 100. So we basically need to multiply the signal by t 100 times and use the property over and over. But we are smarter than that and we can do it super fast. The Fourier transform of xt is x omega. If you multiply xt by t for the first time, you get this j derivative in the frequency domain. Now if you multiply it by another t, you basically need to apply j derivative to the Fourier transform in the previous step. J is multiplied by j and we get j squared. The derivative of derivative is the second order derivative. So if you multiply xt by t squared, you get j squared and second derivative. You can easily extend this argument to any number of multiplication by t. So if we multiply xt by t n times, we get this. Let's use this property and replace t by t to the power of 100. Here we go. The last step is to shift the time by 1 unit and use the time shifting property, where t0 is 1. Done. Next example. If the Fourier transform of xt is x omega, what is the Fourier transform of this signal? To solve this example, first I use the conjugation property, then convolution in the time domain, next time domain differentiation, and finally multiplying by this complex signal and use the frequency shifting property. Let's start with the conjugation property. Then let's use convolution property. Convolution in time is multiplication in the frequency domain. So if we convolve xt conjugate with xt, their Fourier transforms get multiplied in the frequency domain. Next step is to apply differentiation and use the time domain differentiation property. So all we need to do is to multiply the Fourier transform by j omega. Finally, let's multiply the signal in the time domain with this complex exponential function and use frequency shifting property. Here, omega naught is 5. So we basically need to replace omega by omega minus 5. Here we go. Done. Next property is duality. If the Fourier transform of xt is x omega, the Fourier transform of capital Xt is 2 pi multiplied by a small x minus omega. Example. If the Fourier transform of sine t is 2 over j omega, what is the Fourier transform of 1 over t? To use duality, the functions need to have the same form or the same shape in the frequency and time domain. The only difference is, in the time domain, capital X is a function of t, but in the frequency domain, capital X is a function of omega. In this example, x of omega is this. So if we have the same function in the time domain, i.e. the variable is t, not omega, based on the duality, here is the Fourier transform, where a small x is the original signal in the time domain. So the Fourier transform is 2 pi multiplied by the small x, which is this guy. Just we need to replace t by minus omega. In this example, we are interested in 1 over t. So we should get rid of this constant by multiplying both sides with j over 2. 2 is cancelled by 2 and j is cancelled by j, and we get 1 over t in the time domain. 2 is cancelled by 2 here, and here is the final answer. Next example. What is the Fourier transform of this signal? To solve this example, first I'm gonna use duality. Then I will multiply the signal with this complex exponential and use frequency shifting property. From the table of pairs, we know the Fourier transform of e to the power of minus 3t ut is 1 over j omega plus 3. Now look at this guy and this guy. They have basically the same shape, but the first one is a function of t and the second one is a function of omega. To find the Fourier transform, we can easily use duality as the shape of both functions is the same. So the Fourier transform is 2 pi x minus omega. This guy is our small x, just we need to replace t by minus omega. This minus is cancelled by minus omega and we get this. Finally, we need to multiply the signal with this complex exponential function in the time domain and use the frequency shifting property, where omega naught is 2. So we just need to replace omega by omega minus 2. Here we go. Done. The last property that I want to cover in this tutorial is the time domain integration. First example. Prove this property. We can easily show this integral is equal to xt convolved by the unit step function. Let me explain why. Based on my tutorial on convolution, this convolution can be replaced by this integral. Let's plot this signal. Please note the variable in the integral is tau, not t. Here is u of tau, which is 0 for negative tau and 1 for positive tau. If we shift tau by t unit, we get this shape. And finally, if we scale tau by minus 1, the signal gets reflected around the y-axis. So minus t goes to t. If you have no idea what I'm talking about, please watch my lecture on signal transformations. This is basically the same as this one. Let me write it in a consistent form. As you can see, the signal is non-zero for tau less than t. So we can say the integral is non-zero from minus infinity to t. Also, during this interval, this step function can be replaced by 1. So we basically prove that xt convolved by unit step is equal to this integral. Now, as these two are equal, to prove the time integration property, we just need to find the Fourier transform for xt convolved by ut. Let's assume the Fourier transform of xt is x omega. Also, in one of the previous examples, we prove the Fourier transform of ut is this. Now let's do the convolution between x and u. Convolution in the time domain is multiplication in the frequency domain. Here we go. To simplify the answer, multiply x omega by this, and then by this delta function. This function is non-zero only at the origin, so based on the equivalence property which I covered in the elementary signals lecture, this term is only non-zero at omega equal to 0. So here's the Fourier transform of xt convolved by ut, which is the same as this integral. We are done with the proof. Next example. If the Fourier transform of xt is x omega, what is the Fourier transform of this integral? Let's compare this integral with the integral in the time integration property. If you call this guy ft, this is basically ft over 3. In fact, I just need to replace t by t over 3. That's it. Now to solve this example, let's start from the time integration property. Then we need to scale the time and use time scaling property where a is 1/3. So if we scale t by 1/3, we just need to multiply Fourier transform by 3 and replace omega by omega over 1/3, which is 3 omega. Here we go. Done. Last example. What is the Fourier transform of this integral? To solve this example, first let's break this exponential function into two terms. Now we can use the table of pairs to find the Fourier transform for this guy. Then we need to multiply it by this complex exponential function and use frequency shifting property. Finally, we can apply time integration property. Based on the table of pairs, the Fourier transform of this signal is 1 over j omega plus 5. Now let's multiply the signal in the time domain by this complex exponential function and use the frequency shifting property where omega naught is minus 6. So we basically need to replace omega by omega minus 6, which is omega plus 6. Last step is to apply the integration and use the time integration property. This guy is our x omega. So by applying the integral in the time domain, we get x omega over j omega plus pi x at 0, i.e. replace omega by 0, multiplied by delta omega. Done. Okay, that's all I want to say in this tutorial. Now you can definitely call yourself a master of Fourier transform. Thank you very much for giving me your time and watching this long tutorial. You are the best of the best. Don't forget to subscribe to my channel and see you guys in the next video. Cheers!